All right, we're going to jump into a very interesting topic today, and we're going to tackle inverse functions. And inverse functions are pretty much, I think you know, your natural intuition can take over here and kind of lead you to the whole concept behind an inverse. The idea of an inverse, or a sometimes we just call it an opposite, causes the actions of certain functions to be reversed. Okay, so instead of, for instance, just in common day life, instead of going forward, we'll go backwards. Instead of going left, we're now going to go right. We're just going to reverse the process, create an opposite effect. In other words, we're going to undo the actions of certain functions. Okay, so here's a fairly lengthy problem, but we're going to run through it a little bit, and we're actually going to skip part B just for fun there, to save some time. But what I want to do is I want to tackle part A, and I'm actually going to probably scoot down here just to make sure I got enough room to fit it in. They want me to calculate f of 5 first. And so this is good review from last week, and I'm going to substitute a 5 in for the x right up here. And let's see, so it's 3 times my 5 plus my 7, all divided by 2. 15 plus 7 is 22, and if I divide by 2, I get 11. So f of 5 is equal to 11. Now, similarly speaking, let's evaluate g of 11. So I'm going to go to the next function over here, and I'm going to substitute my 11 in for that x. So I got 2 times 11 minus 7, being very careful to try to make this as neat as I can with my substitutions. 2 times 11 is 22. 22 minus 7 is going to give me 15. And 15 divided by 3 gives me 5. So something interesting happened here. What you'll notice is that f of 5 equaled 11, but g of 11 equaled 5. In other words, and I haven't taught you how to create or find an inverse function, but what we're realizing here is that g is the inverse function of f, and in other words, f is the inverse function of g, and they basically undo each other. What you'll notice here in f, ask yourself what's really going on. We're taking x, we're multiplying by 3. You'll notice in this other equation we're dividing by 3, so you quickly realize that multiplication and division are inverses. The first function, f, is dividing by 2, whereas g is multiplying by 2. F is adding 7, and g is subtracting 7. And again, addition and subtraction are inverse operations, so they're undoing each other. Let's go ahead and let's try c here really quick. F of negative 3. If I substitute it into that x, I'd get negative 9 plus 7 is negative 2. If I divided by 2, I'd get negative 1. And let's evaluate g of negative 1 as they've asked. So I'll substitute the negative 1 into there. And negative 2 minus 7 is negative 9. And if I divide by 3, I get negative 3. Again, what was the input for f became the output of g. And vice versa, the output of f became the input of g, and that's how you really know whether they're inverses or not. Okay, let's try another one here. They want me to calculate, and here's a composition of functions. Okay, again, really good review from last week as we entertain and develop a new concept here today. First thing, we're going to go backwards. We're going to take the 5, we're going to substitute into g, and then we're going to substitute into f. So first things first, g of 5 is going to be 2 times the 5 minus the 7 all over 3. Let's see, 10 minus 7 is 3. 3 divided by 3 is a 1. Okay, now I'm going to plug that answer into f. So I need to evaluate f of 1. And 3 times the 1 plus the 7 all over 2. And let's see, 3 plus 7 is 10. 10 divided by 2 is 5. So I got 5. Notice, guess what? We started with a 5 and we ended with a 5 because you plugged it into g, it performed certain actions or certain operations, as we like to say, and then by the time you plugged that answer into f, f was undoing or reversing all of the actions performed by g, and that's why we ended up with the same thing we started with. Okay, now part E is very interesting. They said, hey, without doing any calculations, you want to take a wild guess at what f of g of pi is? Okay, your final answer is going to be pi. You're going to be right back to where you started because whatever g does to pi, f's going to end up undoing it, kind of like undressing it almost, and you're right back to where you started. Okay, so this first sentence here just really emphasizes what we were talking about on that last slide. We said the two exercises, oops, okay, yes, the two exercises in example 1 are inverses because they literally undo one another. Emphasis on that magical word undo. Okay, now the general idea of inverses is shown in this mapping, okay, and it looks like a lot of hectic chaos here, but we'll try to sort it out, okay. So basically we're starting with point A, and we're going to substitute A into function f, and our output is a b. So we started with our input of a, and we got an output of b. And that became the range, as we talked about 2 videos ago. Now, what if you took that b and you substituted it into g? Well, g would basically undo or reverse whatever actions were just performed, and you'd be right back to where you started at a. So it's just kind of like a big circle, and you land back to where you started. So take the time here and hit the pause button and make sure that this diagram is very thorough and detailed. And we're going to emphasize one more thing before we move on here. Let's emphasize that the domain of f is equivalent to the range of g. They are one and the same. Okay? And vice versa. The range for f is equivalent to the domain of g. And that's true for all inverses. Okay? It'll be true as long as f and g are inverses of each other. All right, real quick, before we jump into exercise 3, I've imported a real important statement here regarding the notation that we like to use. All right, so let's say that y equals f of x, that represents the original function. Okay, we're going to use some special notation, and it's going to look like an exponent, kind of. This represents the inverse function of f. Okay, put a special note in your notebook here. The -1, although it's in the same position that the exponent would be, is not an exponent. Okay, it just kind of takes on the same position, but it's a special symbol, notationally speaking, that represents and tells whoever's reading your paper that you're referring to the inverse. Okay, so example number 3 here, we've got a linear function, 2/3 x minus 2. You got a slope of 2/3 and a y-intercept of -2, and it's drawn for you. I think you'll agree we do have a y-intercept of -2, and then we went up 2 over 3, up 2 over 3, and created that linear function. Now we're going to use this graph to answer the following questions. What is f inverse of 2? Well, it's a little tricky here, but I said to myself, well, if the 2 is an x value for f inverse, then that means 2 is going to be a y value for f, and that's this picture is of f, remember. So I looked for a y value of 2, which was right here, and what you'll notice is that point right there is telling me that f of 2 equals, let's see, or I'm sorry, f of 6, scratch that, let me scribble that out, f of 6 equals 2, and since f of 6 equals 2, then that means f inverse of 2 equals 6, just the opposite. Okay, same thing going here. We'll practice another one. We want to say if -4 is the x value for f inverse, then that means -4 is going to be the y value for f. All right, so I'm looking for a y value of -4, which looks like it's right there. And so what that dot right there is telling me is that f of, let's see, 1, 2, 3, f of -3 equals -4. Therefore, f inverse of -4 has to equal -3, just the opposite. We just kind of reverse the process, so to speak. Can you determine the y-intercept for f inverse? Now, just keep reminding yourself, you're staring at a picture of f. And so f's y-intercept is -2, but that's not what they're asking for. They're asking for f inverse's y-intercept. Well, do you see this point right here? Okay, that point right here says that f of 3 equals 0, which implies that f inverse of 0 must equal 3. All right? So we're going to say, and if you plotted 0, 3, it would be right here. And so we could say that the y-intercept of f inverse is at 3. Let's see, it says on the same set of axes, draw a picture of f inverse. And you know what? I've seen a lot of students in the past that said they'd rather do part C before they did part A or B. And I don't blame you a bit. I think maybe we could have drawn this graph first, and it would have made part A and B a whisker easier. Let me pull up a different color here so it'll stand out. Basically, I'm going to take every ordered pair that fell on this original graph, and I'm going to do its inverse. So let's start with this lower left-hand one. That's negative, let's see, 3, 4, 5, 6, -6, 1, 2, 3, 4, 5, 6. Ooh, -6, -6. So that's actually going to stay the same. And then this point here is going to become -4, -3. 0, -2 is going to become -2, 0. We're just switching the x's and the y's. We said that 3, 0 is going to become 0, 3. And let's say that 6, 2 is going to become 2, comma 6. And I'm going to do my best to draw a straight line. Okay, there it is. And this green guy is a picture of F inverse. We just took all the ordered pairs and we reversed or flip-flopped the x and y values. All right, okay, we're going to work off a table of values, which I think you're going to appreciate more than the graph we did on the last one. They've already generated a table of values for x squared. We could have done that. You know, we could have gone to our calculator and plugged in y sub 1 equals x squared, and we could have gone to the table, and we would have generated the same table of values that they've created for us here. But they were really nice to us, and they saved us some time. We're going to generate a table for the inverse, just like they said, by switching the ordered pairs like we did in the last example. So this ordered pair is going to become the x value is now 4 and the y value is negative 2. And then we got an x value of 1 and a y value of negative 1, 0, 0, 1, 1, and then 4, comma 2. So I just took the ordered pairs that were above and I flip-flopped the x and the y's. They just reversed each other. All right, let's go ahead and plot those points. Let's see, 1, 2, 3, 4, negative 2. And let's go 1, negative 1, 0, 0, 1, 1, and then the last one was 4, 2. And what I've created is kind of a sideways parabola here. All right, so that's my answer to part A. It was just a nice sideways parabola. And now they ask me, you know, what do you notice about the graph of this function's inverse? Well, first of all, the first thing I noticed to myself was that it doesn't pass the vertical line test, so it's no longer a function. That's one thing we could say. All right, it fails the vertical line test. Here's the more valuable concept that I want you to take away. I want you to visualize a diagonal line that cuts right through the middle of the graph from corner to corner. That special line is the equation of y equals x. It's a very standard linear function that cuts diagonally across the paper. These graphs are reflections of one another. Okay, so we say that F inverse is a reflection over the line y equals x. And that'll be true for all inverse functions. If any time that we're dealing with f and f inverse, those two graphs should be symmetric with respect to that line. In other words, they are reflections over that line. So that's a real important statement. Make sure we get in our notebooks right there. Okay, the very last thing I want to throw at you tonight is just an existence theorem. And basically it says if you want to prove whether an inverse function exists or not, you know, truly as a function, and not only does the original pass the vertical line test, but f inverse passes as well. All right, so let's make that note here that we want to make sure that both f of x and f inverse pass the vertical line test, okay? And we saw in our last example that that wasn't the case. Although the original function passed, the one that I drew in blue failed the vertical line test. So we want to make sure, a lot of times this will be a question on a quiz or a test. They'll just ask you, here's a picture of f. Do you think his inverse will be a function or not? And in order to figure that out, we're going to say, this definition right here, a function will have an inverse that is also a function if and only if it is one-to-one. Okay. In other words, on our last video we said one-to-one means it's got to pass the horizontal line test. So let's practice an example right here. All right. Let's see here. Here's a picture. Let's give him a name. Let's call him f. First of all, do you think f is a function? Hopefully you said yes, because he does pass the vertical line test. And so the next question becomes, do you think that f inverse will also be a function? Question mark. So even though f is a function, what you'll notice is that f is not one-to-one. In other words, he fails the horizontal line test. And we could say, well, because f fails the horizontal line test, then that implies that f inverse is not a function. And it's as simple as that. You don't have to do any more work than that. Just visualize your horizontal line test and know how to interpret it. All right, real quick before we wrap up and part ways tonight, I just want to really summarize what we've done tonight. We've thrown a lot at you. The idea that an inverse simply undoes or reverses the process and actions of one function. And to really summarize it here, we're going to say, well, if f of a equals b, in other words, a is the x value, the input, and b is the y value, the output, then that implies you instantly know that f inverse of b has to equal a. Okay, and now b is the x value in the input and a is the y value or the output. So they just flip-flop. Okay? In other words, if the ordered pair A comma B sat on the graph of F, then you automatically know that B comma A is an ordered pair that sits on the graph of F inverse. And that's basically what it boils down to in when we're talking about inverses, and I think that'll really help you in class tomorrow. In other words, if you know the domain for F, then you already know the range for F inverse because they're one and the same.